Articulate interactive visual guidance for demonstrated rotational degrees of freedom in mobile AR. Mobile augmented reality offers a powerful way to provide users with precise guidance on spatial configuration tasks that are important to different real-world applications. In some cases, we can formulate the task as the configuration and motion of some object with different spatial degrees of freedom, in which case our challenge is to help the user translate and rotate the object to achieve some goal. In other cases, the task may involve recording some particular distribution of images, in which case our challenge is to help the user translate and rotate the camera to achieve a particular goal. In both of these scenarios, the user has control over some spatial degrees of freedom in the scene. For object configuration tasks, those degrees of freedom are determined by how the object can move. And for camera configuration tasks, while there are technically 6 degrees of freedom for the camera, we are often more concerned with something like capturing an object from many different angles. And in this case, the guidance we need to offer the user amounts to something like rotational degrees of freedom centered on the object of interest. Our contribution is a method that infers these critical degrees of freedom directly from observation of the user behavior. Let's see how this works in practice. In this example, the user is tasked with rotating their hand into a particular configuration, and by inferring the center of rotation, we're able to offer them visual feedback corresponding to the angle of their wrist joint. For an example of camera configuration, here we have a scenario where the user is capturing a 3D model of the subject. And by observing how the user is moving the camera, Articulate is able to infer where the subject is and uses that information to quickly produce a coverage map that visualizes which angle they've already captured and which angles they still need. A key insight of our work is both scenarios can be addressed by inferring an ideal choice of coordinate system for representing the given configuration task. To see what this means, let's take a closer look at an object configuration task related to our previous work on capturing time-lapse of the human body. In that work, we built a healthcare application that lets people track long-term changes of their body over time. And in this example, our AR guidance helps users photograph their own head from a specific position and angle. However, our mobile phone only ever sees part of the head at any one time, so we represent the part that our depth camera senses with this blue line. Now, let's say that we want to direct the users toward a new configuration where they rotate their head without moving their body. The goal of our guidance is to convey the transformation between what we have and what we want to the user. We could map the rotation part of this transform to something like the rotation of this crosshair, and the translation part to something like the offset between the two rings. But notice that this decomposition depends heavily on our choice of coordinate system. If we place our origin at the center of our observed geometry, then a simple tilt of the head turns into a tilt followed by a substantial translation. And based on this feedback, a user would erroneously conclude that they need to move their entire body. To correctly infer that they only need to rotate their head, we must align the origin we use when factoring our transformation with the head's natural center of rotation, which sits in the neck, far from the geometry our device can actually see. When we correctly identify this natural center of rotation, our guidance aligns with the user's intuitive head movement without any translation. Let's look at the real-world version of our head configuration example. To determine the rotational degrees of freedom for the user's head, we simply ask them to demonstrate some rotation motion over a 15-second calibration window. We then infer the center of rotation that best explains this observed motion, which we can immediately use to provide precise visual guidance to the user. Here, we visualize the average of the observed geometry as a pink sphere. This point is often used as a default origin for transformation calculated on depth sensor data. We can see that it is quite off from the blue sphere, which is our inferred center of rotation in the user's neck. Articulate is not specific to human's head. It works for any geometry with rotational degrees of freedom. In this demonstration, we calibrate for the center of rotation for a human hand, which our method accurately identifies as a point in the wrist. When we use the center of rotation inferred by Articulate, rotating the user's wrist does not affect the ring's position. By comparison, if we use the same default using APIs like ARKit, we see that our translation guidance becomes coupled with any rotations made by the user. So how did this work mathematically? In the left image, the coordinate system is placed at a joint. Here, the transformation matrix has a clean decomposition, M equal R and T. Rotation R and translation T are independent, which aligns with how users naturally think about movement. But now look at the right image, where the coordinate system is at the center of the hand. Now, our transformation matrix includes an offset term, which creates a coupling between rotation and translation. This leads to what we call rotation leakage. When users follow rotation guidance, they unexpectedly need to translate as well, making the interface feel unnatural. Our strategy is to infer the coordinate system that explains all of the user's observation using the least amount of translations possible, which we do in 3 steps. First, we obtain transformations from tracking data as users demonstrate object rotations. Next, we stack this equation into a unified matrix form. And finally, we solve for the optimal rotation center using least square minimization. A full implementation of the Articulate plugin is available on our website. We conducted a user study which shows that visual feedback that uses a Articulate as reference frame leads to significant reduction in task completion time. In our experiment application, users followed 2 visual guidance. As mentioned earlier, the crosshair gives rotation guidance while the ring guides translation. When we use a Articulate's infer center rotation, the ring translation guide stays stable as the user rotates their wrist. On the right side, we use the baseline, which uses the point average as the center of rotation. And without a correct reference frame, the ring guidance moves erratically, making the alignment task much harder. In our second user study, we look at the user's task completion time as a function of how much the coordinate system deviates from our estimate. We found that as the guidance goes further away from the ideal center of rotation, which is shown in the 0 offset in the center, the task completion time goes up. Whether we have an articulate object rotating around a joint or a camera moving around a fixed subject, mathematically they are the same. Both involve identifying rotation around an important axis. Now let's dig deeper into the second scenario. Let's look at an example where I want to 3D scan my advisor so I can import him into Unity as the final boss in my game. Creating accurate 3D models requires capturing all angles of an object. Existing framework like Apple's Object Capture also provides coverage map guidance showing which angle you have captured and what you still need to scan. As mentioned earlier, for this visual guidance to work correctly, the system still needs to know where the center of rotation is. Apple's API lets users tap on simple objects to set a bounding box. But for complicated objects like this telescope, we had to manually adjust the bounding box to set the center of rotation. This manual adjustment can be tedious and error-prone. In the right video, we show a Articulate in action where users can simply start moving around the object, and our system automatically infers the red axis of rotation that helps anchor the coverage map guidance. In addition to mobile devices, we also demonstrated how Articulate can be integrated as a Unity plugin for the MetaQuest Pro. On the left, you see my first-person view from inside the headset. On the right is the same interaction from a third-person perspective as I walk around my labmate to first identify where the center of the subject is before rendering the coverage map. And lastly, we extend our method to handle complex articulate objects that have non-intersecting axes of rotation using an iterative process. Consider this telescope mount with 2 joints. In this case, the center of rotation for one joint is offset from the center of the other. We can handle this by having the user demonstrate each joint separately and mapping each degree of freedom to separate 1D visual guidance. First, let's identify the azimuth movement. Let's add axis 1 and then provide a small demonstration. Here, the infer vertical axis of rotation is shown as the blue line perpendicular to the azimuth motion. Now, let's load a reference image to guide users in matching rotation along this axis. You can see how the one-dimensional slider maps to the current angular position, where the movable dot shows the current degree of freedom value relative to the reference point. For the second degree of freedom, let's fix the first one and repeat calibration. Again, we define new axis of interest and then do a quick demonstration. Traditional AI systems typically use fixed reference frames that don't account for these object-specific, user-intuitive center of rotation. This creates a disconnect between how the system provides guidance and how users naturally think about manipulating the object. So in conclusion, our method offers a simple and extensible strategy for factoring complex articulation guidance into manageable parts that can be mapped to easily interpretable visual guidance for users. We believe that this technique will prove to be a useful tool for new applications of mobile AR as the mobile tracking technology continues to evolve. For more details on our method, please see our paper. Thank you.